Hi everyone, this is Mrs. GA, and today we're going to be modeling with trigonometric functions. So a few things to consider before we start our modeling. First is maybe a new vocab word for some of us, and it's the word sinusoidal. So sinusoidal means having the form of a sine curve. So we know that that means kind of making that wave shape. However, it can be modeled with either the sine or cosine function. So I don't want you to think that sinusoidal means it can only be modeled with sine. Sine or cosine can be used to model this type of pattern. The second thing is kind of a reminder that amplitude is half the distance from the maximum to the minimum. So amplitude is going to play a big role when we're modeling, so it's important to remember that it is half the distance from the maximum to the minimum. And last, period, which will also play a big role when we're modeling. Just want to remind you how we can manipulate the period, and that's by using this little formula, and it was 2 pi over k, or really that's just 2 pi times the reciprocal of this horizontal stretch or shrink. So remember, k is this number that is being multiplied to x. So you essentially take 2 pi, which is the original period, and you multiply it by the reciprocal. So remember that this is the little formula we can use, and we can use that to help us make our models. Okay, let's look at this first example together. So this says the number of hours of daylight per day varies sinusoidally throughout the year. In San Francisco, the longest day of the year is about 14.5 hours, and the shortest day of the year is about 9.5 hours. They would like us to create a function called d of t that models the number of hours of daylight in terms of time, t, in months. And we're going to here assume that t equals 0 represents the shortest day of the year. Okay, so for these, it can be useful to sketch a graph, and when we do that, it can also be really useful to actually label what our x and y values represent. So I'm going to zoom in on my little graph here, and so remember that our x-axis represents time in months, and our y-axis represents the hours of daylight per day. So hours of daylight. Okay, so a couple important numbers here in terms of our y-axis. We know that the longest day is at 14.5 and the shortest day is at 9.5. So those are going to be two critical values for us. So just so we don't have to worry about being too meticulous with our scale, I'm going to kind of do this little squiggle right here, and then we're going to call this 9.5, and we're going to call this 14.5. Okay, so we're just doing this to help us get an idea of where some of our important values are. And then, of course, the other important value is going to be that midline, the exact middle between the high and the low. So the midpoint of between 14.5 and 9.5 is 12. So remember, for these types of graphs, I like to sometimes sketch in maybe a midline. So I can sketch in a midline like this, and a maximum and a minimum to help us sketch our graph. Okay, so then the next thing to consider is what's our period, or how long does it take for a full cycle to reoccur? So we can kind of just use common sense for this. So we know that, throughout the year, there's really one full cycle of this daylight pattern. So we know that in the winter, the days get shorter and they eventually reach a really, really short day, and then they start getting longer and longer. And then kind of in the peak of summer, you'll eventually hit that longest day, and then, of course, it will turn back around the other way. So to kind of draw a really quick sketch, we know that t equals 0 is going to represent our shortest day. So that's going to represent, or we're going to put our first point here. And we know that since it takes a full year to repeat a cycle, that our period is actually going to be 12 months. So we can do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we know by the end of 12 months, it's going to return back to the minimum. So that means that halfway in between, it will be at its maximum. So we can go 1, 2, 3, 4, 5, 6. We can go up to the maximum. And then if we have the next 6, 1, 2, 3, 4, 5, 6, it brings us back to the minimum. And we can even do our midway point. So if I go 3 months in, I'm at the middle. And then I'm at the maximum, and then I go 3 more months, and I'm back at the middle, and then I return to the minimum. So this shows 1 full period of our daylight cycle. So here, using our graph, I can determine 2 of the most important features of any function. First would be the amplitude, which remember is the distance from the midline up or from the midline down. So in this case, our amplitude is 2.5. And then, of course, our period as well is very important. So here our period is 12 months. And then I'm also going to note any other changes that we might see. So one thing we notice is that this does look like maybe it could be modeled best with cosine. And of course, you can choose sine or cosine. But since I'm starting at a low point, I am going to use cosine as our function. But remember, cosine usually starts at a maximum. So that means that we also have to accommodate for a vertical reflection. And then we can see that our midline, which is usually at 0, is actually up here at 12. So we can say that we have a shift up 12. So these are all of the things I need to account for in my function. Now again, we could use sine to model this, but if we use sine, then we would also have to do a shift, which wouldn't be the worst thing in the world, but if we can pick one that will be easier, it would definitely be cosine. So let's start with d of t. So remember, that's what they would like us to call the function. So the first thing we're going to account for is that vertical reflection. So I have a negative, and then we do our amplitude, which is 2.5, and then we decided to use the cosine of, and now we need to adjust for the period. So I need to figure out what value should I multiply to x. And remember, I can use this little formula. I can say 2 pi divided by k should equal 12. So that means that k should be pi over 6. And then I have x, and let's see, what have we accounted for? We've accounted for the amplitude, the period, we've used cosine, we've done our vertical reflection, and last we just need to shift our graph up 12. So we just say plus 12. And there you have it. So we could use this model to essentially figure out how many hours of daylight we would have at any month. Okay, we're going to try one more problem together. So this problem says, the pendulum of a grandfather clock swings back and forth infinitely as shown in the image below. So this is the pendulum, and you can see that it's kind of doing this swinging motion. At its furthest point to the left or right, the end of the pendulum is 8 inches from its central location. So I'll highlight that. And that's at the furthest position. And again, that central location is right here, shown in black. From the far left position, it takes 2 seconds for the pendulum to swing and return back to that position. So it takes 2 seconds to start here, make it here, and back. Then they ask us to create a model, P of t, that models the distance of the pendulum in inches from the central location. Assume that the far left position is t equals 0. Okay, so I am going to start by labeling my axes. So we know that t, or x-axis is t in seconds. And we know that our y-axis is the distance from the center in inches. So here, this one is going to be a little bit trickier, and we really have to make sure we're careful when we're reading and interpreting this information. So we say that we're going to call t equals 0 right here when our pendulum is at the far left position, and the position is going to be 8 inches from the center. So we know that it takes 2 seconds for the pendulum to swing all the way and return back to its position. So since it takes 2 seconds from here, we can assume that it's going to take 1 second for it to reach this position. And if you think of this, well, at 1 second, it is also 8 inches away from the center, because from its furthest position, either to the left or right, it's 8 inches. So just using this, let's see if we can mark this on our graph. So here is 1, so I'll mark a couple seconds here. And for the inches, I'll count by 2s. Okay, so we know that at t equals 0, we are 8 inches away. So that would be right here. And then and let me scale this by, I'll scale this by 1/4 of a second. And then we know that by t equals 1, we are back at 8 inches away. And then we can assume that means that at t equals 1/2, we are in the center, which means we are 0 inches away from the center. So that would bring us down to here. So you can see that this kind of gives us a graph that looks something like this. So using this, we see that our maximum value is at 8. Our minimum value is at 0. Of course, that's when it's in the center. And although it takes 2 seconds for it to go all the way to the right and all the way to the left, it only takes 1 second for it to repeat this pattern of how far away it is from the central location. So that's why it's really important that we understand we're modeling the distance of the pendulum from the central location. Okay, so it actually only takes 1 second to repeat a full cycle of this. So it's really just a swing from left to right. So looking at our picture, we can use this to help us find the key information for our function. So we can also take the step of saying, okay, if our maximum is 8 and our minimum is 0, our midline is at 4, which means our amplitude is 4. Which again is the distance from the midline up or the midline down. We can see that our period is 1 second. And then let's look at what else we should adjust for. I see that since I'm starting at a maximum, it would be easiest for us to use cosine as a function. I can see that we do have a vertical shift. So since our midline is at 4, we know that we need to shift our graph up 4. I don't see a reflection of any type, and we don't have a horizontal shift if we're using cosine. So we should be ready to create the function. So remember, they would like us to call this function p of t. So again, our amplitude is 4. We're choosing to use cosine. The way that we would turn our period into 1, so again, if you need to, you can set up this little equation, right? So we know that k equals 2 pi. So we have to multiply our x value by 2 pi, and then we do need to shift our graph up 4. So this is one way we can make this function. And just for practice, let's say we chose to use sine. So if we choose to use sine as our function to model, our amplitude and the period are the same, and we are still going to shift it up 4, but you'll see that for sine, remember sine always starts at the midline, so we would have to shift it to the right 1/4 of a unit. And then if we're shifting to the right and we're starting here, you'll notice that our graph goes down instead of up, so we would also have to do a vertical reflection. Alternatively, we could also just shift it more and then not do a vertical reflection. There's really an infinite number of models we can make for this, so it's really up to you. But let's say we decide to start it here, so we shift it to the right 1/4, and then we're going to reflect it vertically so it goes down first. So we can make our function adjusted for that. So again, we'll do negative for the reflection, 4 for the amplitude, and again, this is if we decided to use sine. We still need to change the period, and we would do that with a 2 pi right there, and then I'm going to do an extra parenthesis, and then we're going to do x minus 1/4. So remember, the shift and the shrink need to be separate, and you can actually leave it like this. You don't need to distribute it, although you can if you want to. And then last, we do still need to shift it up 4. And there you have it. So remember, for these, if you compare the two functions, obviously it's a little bit easier to use cosine here because you don't have to do the shift or the reflection. So it's important that you're strategic, but whichever way really jumps out at you is fine. So either of these answers are totally acceptable. Okay, that is all for today's video. Thank you so much for watching.